SwayamPrabha. Digital India. Educated India.
So, this particular module we are going to discuss about cylindrical cup deep drawing. Okay. So, this is a new model, and then let us see how to develop some expressions, equations for predicting certain things in deep drawing, sheet cup deep drawing. So, we are going to specifically discuss only about cylindrical cup deep drawing in this particular module. So, this cylindrical cup deep drawing, we already discussed this briefly in the first chapter. This is how the process will look like. This is schematic. You will see that so initially we have a flat sheet. Initially we have a flat sheet like this, and on top of that you are going to rest a punch, and before punch starts moving down, we have to clamp the sheet on the die. Okay, that will be done with the help of a blank holder. Okay, and we know that we have to give appropriate blank holding force. We know how to get blank holding force, that we already discussed in the stamping analysis. So, we have to give appropriate blank holding force so that the inward movement of the sheet can happen with some restriction due to the contact friction between the sheet blank holder and the die. Okay. And when the punch moves down, so you will see that basically the cup bottom is formed first. This is your cup bottom, we know that. This is your cup bottom that is going to form first. And after that, if we see, the entire process is all about converting the flange region into cup wall. So, this is your cup wall region, that also we know already, and this is your flange region of the cup. So, once a cup bottom is formed, that can form just when the punch touches the sheet. A little movement, maybe 1 mm movement itself is sufficient to create the cup bottom, and after that your cup wall will form, and that is going to happen due to the inward movement of this flange. So, it is all about converting a flange into your cup wall in this way. So, it is going to move like that, and the schematic shown here is a partially drawn cup. That is why you have a cup wall and a flange region. Okay. If you make the punch to move down further, then the entire flange region will become a cup wall. Okay. So, and previously we have already discussed what is the mode of deformation or maybe state of stress in the cup wall and in the flange region. We have discussed these two cases. Okay. So, I am going to divide this deep drawing of circular cup. Okay. Deep drawing of circular cup can be viewed as two different processes. Of course, these two happen continuously, but you can view this as two different operations or process. One is stretching sheet over a circular punch. That is what I was telling you initially, that the cup bottom is gets stretched below the punch, and drawing an annulus inwards. So, drawing an annulus inwards is basically like converting this flange region into cup wall. So, you are pushing you are drawing this annulus region. Annular region means this entire, this diametrical region in the inward direction. Okay. And the cup wall is going to transmit force between these two regions. Cup wall is going to transmit force between these two regions. Okay. So, this is schematic. From the schematic and from this view, we can in fact say that the deep drawing is nothing but drawing an annulus inwards. And if you see the top view of this, okay, if you see the top view of this, that is what is given in the right side diagram, is a drawing of an annular flange, I have said. Okay. So, you will see that so this is your outer radius of your that is R naught. This is you can say this is O, this is R naught. So R naught is basically your initial radius of the sheet, you can say. Okay. And Ri is basically the inner radius. Okay. Or you can also say this equivalent to punch radius. You can also say this as a punch radius or punch dimension, you can say, or you can also convert that into diameter and say punch diameter and outside diameter, you can say sheet diameter. So you can see that the punch is actually perpendicular to the plane of this diagram and it is moving downwards, let us say. Okay, the sheet is actually getting a inward movement. So this part is actually going to move inwards, okay, so that it forms a cup. So there has to be an appropriate diameter or radius of the sheet because of which you can form a successful cup. Okay. So larger the blank or smaller the blank may not be sufficient, okay, to make the actual cup which we want actually. Okay. So we have to keep that in mind actually. So if you see that we can divide this flange into maybe like 3 different locations I mentioned, A, B and C. A at the edge of the flange, B somewhere in the middle and C in the die corner. C is in the die corner, you can see here. So this is your C, this is your B and this is your A, you can say. Okay. So I have located it here, A, B, C locations. These 3 locations are there in the entire flange region, you can imagine. Okay. And the state of stress in the A region and B region are mentioned here. This we already discussed in other chapters. So A region, there is no sigma R here. So sigma R is basically radial stress along the radial direction, along R direction, along R direction. Okay. By the way, R is basically any radius, okay, in between your Ri and R naught. Okay. So you pick up an element, let us say here, this element, blue color element which I mentioned, it is at R radius from the axis. Okay. So R can vary between Ri and R naught, you can imagine like that. And let us go to this A. So you will see that along the radial direction, you will have sigma R. That sigma R is missing here because it is at the edge of the flange. Sigma R will not be there at the edge of the flange. If you move inward direction, somewhere in the middle region, you will see that you will have both sigma R acting in this direction and sigma theta is in the compression direction. Okay. So sigma theta is inward arrow mark I put, which is basically compressing type, and sigma R is going to be pulling type. And C would be at the your die corner region. Okay. So these 3 locations are important for us. And what I am going to do now is I am going to consider an element in the flange region and we are going to apply force equilibrium. So let us pick up an element in the flange region, okay, and I have already plotted all the stresses available in this particular element. You can imagine that this element is basically this in this location. In this location you have this element, let us say. So now you will see that so this element has a radius of dr, which is at r distance from the mid, and this element subtends an angle of d theta, okay, with respect to the axis, and you will see that there is one sigma r radial stress and there is one sigma theta which is a circumferential stress, and we know that at a gap of dr distance, let us say from this to this, there will be some change in sigma r, which you are going to call it as sigma r plus d sigma r. And if you see from thickness direction, okay, so the thickness direction, though we say T naught as the initial thickness, okay, during deep drawing you will see that in the flange region, okay, there will be slight thinning in the die corner somewhere here, and there will be slight thickening in the edge of the flange, T plus dt. Okay, that is why I mentioned it T plus dt. So and here it is T. So these are the stresses on an element at radius r. Okay. So this r is nothing but this r only. Okay. So now what I am going to do is I am going to apply equilibrium for this element, and if you do that you will get this particular equation. You can look into it. It is sigma r plus d sigma r for this one into T plus dt. Okay, that is your thickness here, into r plus dr. R plus dr is this total radius of this into d theta. That will be equal to, you will take this sigma r tr d theta, and there will be one component of sigma theta along r direction. So that is going to be 2 sigma theta dr sin theta by 2, which can be written as sigma theta t dr d theta. You can in a simplified way you can write this. So basically sin d theta by 2 can be written as d theta by 2, and you can write it in this way, sigma theta t dr d theta. Okay. And of course you can simplify this further. So I have not done it. So one can do this. If you do this, it will reduce to one simple equation, d sigma r by dr plus sigma r by t d theta by t minus sigma theta minus sigma r divided by r equal to 0. Okay. So and this is for a non-strain hardening material. Okay. You don't consider strain hardening in this equation, and it's a frictionless case. So no effect of friction. Okay. These two are not available in this equation. So the first part basically tells it with radius how sigma r changes. The next part is going to tell you how t changes with r. You will come back to this. Okay. And then your sigma theta minus sigma r divided by r is equal to 0. So we will come back to this equation now, how to solve this, how to get, basically our idea here is to get a sigma r. Okay. So our idea is basically to get a sigma r, which is nothing but your radial stress. That is the whole idea here. Okay. Because if you get sigma r by assuming any yield criterion, we can get a sigma theta also. Okay. Because these two are principal stresses, we can get sigma theta also. So now before we come to this equation, okay, let us get into some details of this ABC. This ABC point which we have shown here, A is at the edge, B is at the mid, and C is at the die corner, okay, covers the entire blank flange region, and these 3 points are actually shown in the yield locus in this way. Okay. So A point, which is at the outermost edge of the flange, okay, we have said that sigma r is equal to 0. Only sigma theta would be there, sigma r radial stress will end there. Okay. It will not be there at all, it is going to be 0. Okay. So that is why you will see that sigma r 0 means it will fall in the x axis, okay, and it will be on the second quadrant. It is going to coincide with the x axis, this point A. Okay. And we have already seen that at this location sheet will thicken at this point. Sheet will thicken at this point. Okay. So we have already seen this as an example. Okay. And we also, I think, worked out your why sheet has thickened. In fact, the problem also, one problem, numerical problem we solved in the previous chapter also tells that, okay, if you follow this particular mode of deformation, the sheet will have would have thickened when compared to the previous its original thickness. So you should know that at the edge location, at the outer edge, that is why we have said T plus dt. Okay. So you can write the state of stress sigma theta is nothing but minus sigma f, okay, which is known as uniaxial compression, okay, and the sigma f is nothing but our current flow stress, Before reaching current flow stress, it would be your initial flow stress or the yield stress. So now when you go to point B, okay, so we have to pick up a point B in such a way that, basically we are picking up a point B in such a way that the radial stress is equal to opposite to hoop stress. Okay. So the radial stress, your sigma r is equal to minus sigma theta. Okay. Your radial stress is actually sigma r, which is equal to minus sigma theta. That is what we have said in this point B. So they are equal and opposite, and this will give your alpha as, let us say, minus 1. If alpha is minus 1, then you will see that you can get a beta, and at this particular mode of deformation, you will see that there is no change in thickness at this point. Okay. If alpha is equal to minus 1, you can get a beta from Levi-Maser's flow rule, and you will find out that there is no change in thickness at this particular point. So now when you go to point C, radial stress would be maximum at that location, because that is basically die corner region, okay, and it is also expected that sheet thinning is going to happen in this location. Okay. So I mentioned the C point somewhere here. Okay. So this ABC points in the flange region is going to fall on the second quadrant. A, which is going to be sigma theta is equal to minus sigma f, it is going to coincide with the x axis, and you have opposite sign minus. B, we are choosing in such a way that sigma r is equal and opposite to your sigma theta, and at C location you will see that sigma r would be maximum, radial stress would be maximum, and here sheet thinning will happen. So the edge you will have thickening, and at the somewhere in the mid location you will have no change in thickness. So that means thickness strain is going to be 0. And in the dike corner region you will have sheet thinning. So that is the way these A, B, C points are actually characterized. And you will also see that we have already mentioned this particular one in the previous chapter, that okay, so anything below this particular location, below this mode of deformation, you will have thickening, which is what is characterized here, and beyond this in all other beta values you can see that it is going to thin down. So which is basically at the C location there is chances of thinning. So at B basically is we are picking up B in such a way that these two are actually equal and opposite, so there will be no change in thickness. Okay. So this can be compared, this particular characterization, this thickening and thinning which is mentioned here, can be compared with the previous discussion we had. Similar diagram we already discussed. Okay. So all the stress states like this can be represented in terms of let us say for example a von Mises yield locus like this. So now let us go back to this equation. Okay. So now just for a change in this analysis we are going to use a Tresca yield function, which is we have not used until now. We have used only von Mises yield function until now. If you use Tresca yield function, this yield function is already derived in the previous chapter. So sigma theta minus sigma r is equal to minus sigma f naught. Minus sigma f naught is nothing but the initial flow stress, nothing but the initial flow stress. Okay. So why we are saying that is because we are going to now replace this fellow by sigma f naught to get into some details. So now what I am going to do is I am going to make one important assumption, that by considering T is equal to T naught, by considering my T is equal to T naught, okay. So what will happen now by considering T is equal to T naught? Okay, so we will say that in this equation this part will vanish, this part will go away. Okay, why? Because we are saying that there will be some change in thickness with respect to R value, okay, which is not the case here. We are saying that T is going to be equal to T naught, okay, which means a change in thickness is actually neglected in this equation. So you have differential equation is nothing but this first term and this second term, first term and this second term. Okay. So now what we are going to do is, so there is a small change in this equation is not valid here. We are going to say that this equation d sigma r by dr, so d sigma r by dr, okay, this fellow goes, second term goes off, okay, minus sigma theta minus sigma r divided by r, sigma theta minus sigma r divided by r equals 0. Okay. So if you want to integrate this equation, okay, so and by following this boundary condition. What is the boundary condition? We know that at r naught, that means at the edge of this flange region, we say sigma r is equal to 0, right. So and another limit is basically this inner radius, okay, at r is equal to ri, at r is equal to ri, we are going to say that there is some radial stress, that is sigma r is equal to sigma ri. Okay. So if you see sigma r, how is it going to vary? It will be sigma ri here and it will be 0 here. It is going to vary between these two, and let us integrate this particular equation, okay, by taking T is equal to T naught, and by applying this boundary condition you will see that you will get a simple equation, sigma ri will be equal to minus sigma f naught ln of ri by r naught. Sigma ri is equal to minus sigma f naught ln of ri by r naught. Okay. So of course this can be written as sigma f naught ln of r naught by ri. Okay. And because this equation is known to us, sigma theta minus sigma r is equal to minus sigma f naught. So now I am going to substitute the sigma r in this equation and get sigma theta as minus sigma f naught minus sigma r. Okay. So you have to integrate this equation and not this. Let us forget this equation. Okay. This is not correct here. So this equation we have to integrate by considering T is equal to T naught. So there is a second term which goes off. Okay, and you will get sigma theta is equal to minus sigma f naught minus sigma ri. Okay, so in this way, for a non-strain hardening material, of course without friction, okay, the radial stress is given by sigma ri, equation derived here. Okay, and radial stress will give you sigma theta by assuming one yield function. Here we are picking up a Tresca yield function and we are getting it. Okay. So, now in this equation you will see there is one important point, which is what we are going to discuss in the next slide. We have already discussed briefly about drawing ratio. Drawing ratio means basically its initial diameter of the sheet divided by diameter of punch. Okay. So, drawing ratio is nothing but this called as dr equal. Okay. So, drawing ratio is nothing but initial diameter of the sheet divided by diameter of the punch, and this draw ratio will give limiting draw ratio, which we call LDR. Limiting drawing ratio, which we call LDR. Considering this diameter of punch as a constant, then what diameter, initial diameter of the sheet you can keep, okay, to have a successful cup. That will be decided by this LDR. That will be decided by this LDR. So, which means in a way you see that it is R naught by Ri. R naught is nothing but your radius of the sheet, which is nothing but the diameter of the sheet, divided by Ri, which is the inner radius, which is nothing but the punch diameter, is going to give you some way, it is going to define your LDR. Is going to define your LDR. So, we are going to put a condition now, okay, which will give us some value of this LDR. What is that? We are going to say that the greatest stress in the cup wall that it can sustain for a material obeying Tresca is actually sigma F naught. So, in the cup wall, if you see, okay, the greatest stress the material can withstand, if you follow Tresca yield function, is actually sigma F naught itself. So, what we are going to say is, in this equation, if sigma Ri is nothing but sigma F naught, okay, what will happen? Now, if sigma Ri is equal to sigma F naught, we get the largest blank that can be drawn, which is also given by, so this equation I am picking up, which was introduced to you before, sigma Ri is equal to minus sigma F naught ln of Ri by R naught. In this, if I put sigma F naught, you will see that my R naught by Ri is going to be equal to 2.72, which is nothing but LDR is actually exponential 1, E1. Okay. So, I am going to put sigma F naught here, and of course, this minus can be taken care automatically. So, you will get R naught by Ri. So, R naught by Ri would be nothing but exponential 1, which is nothing but 2.72. So, R naught by my R naught by Ri, which is nothing but in a way to describe define LDR, is nothing but 2.72 if you pick up an extreme case of this particular one. Okay, the greatest stress the cup wall can withstand for a material, it should not actually go to that level, but it is the greatest stress. Okay, if it goes to extreme, then the LDR can be 2.72. That means what? If Ri is fixed, suppose your punch radius or diameter of the punch is fixed, you have to multiply it by 2.72 to get the initial diameter of the or initial radius of the sheet, and only if you pick up that particular diameter, you will get a successful cup. Okay. But as I said, this particular value sigma Ri is equal to sigma F naught is too high, and because of that, what I am going to see is instead of this 1, I may slightly reduce it depending on my requirement. I am going to say, let us say LDR is nothing but exponential eta. Okay. And if you take eta as, let us say 0.7, let us say, or 0.62, 0.7, 0.62, let us say 0.7, I get LDR of 2. That means exponential, let us say instead of 1, you take exponential 0.69 or 0.7 or 0.6 you can take, it will give you a value lesser than 2.72. 2.72. Why? Because 2.72 is an extreme case. So, if you pick up an eta value of 0.69, you will get LDR of 2, which means that your R naught by Ri would be equal to 2. That means if you take Ri, let us say radius of the punch or diameter of the punch, let us say you take diameter of the punch as 50 mm. Okay. So, then you multiply that with 2, the initial diameter of the sheet has to be about 100 mm or closer to that. Generally 0.6 to 0.7 you can pick up, which will give you a range of LDR, which is going to give you a successful drawn cup. So, through this derivation, simple derivation, though it is for a non-strain hardening material and frictionless case, we derived expressions for sigma R radial stress and sigma theta, okay, by assuming Tresca yield function. This is the first time we are doing it in this course. Okay, and if you put a condition for sigma R, okay, which is nothing but if it is equal to sigma F naught, then you will get a limiting draw ratio as a particular value, that is 2.72, and is an extreme case. Anything less than that would be better. So if you take a eta of 0.7 or 0.6 in between values, so you may get LDR of the order of 2, which is what is you can refer to. This is the simplest way to calculate your limit drawing ratio. So now what we are going to do is, so this equation has been obtained, and from this equation we got sigma theta also. So what we are going to do is, we are going to modify this sigma r by considering strain hardening effect and friction effect. Okay. So modification of radial stress with the effect of strain hardening, that is the next one. So now what is going to happen is, because of strain hardening, we know that the flow stress will increase, right? The flow stress will increase, and if you pick up this flange region, if you pick up this, we will go to this diagram. If you pick up this particular flange region, okay, so you will see that at different locations you may get different levels of flow stress, okay, and it will be non-uniform. It will be non-uniform. So you can imagine that like previously we discussed, so you can maybe like you can put a lot of circle grids on the surface, and maybe you can get strains at different grids, and from there you can get sigma bar, from there you can get sigma 1, 2, 3. So all those things you can do in this flange also. Finally you will see that the flow stress is going to be get distributed in a non-uniform way in the flange region. So how are you going to quantify it is by taking an average flow stress in the entire flange region. So which means you can imagine that from the strain evolution you can get maybe like epsilon bar, and from there by using some flow stress model you can get some sigma bar, and you can just take an average value, you will get some average value of your flow stress in the whole flange. Now what I am going to do is, this is my original equation, I am going to just modify the sigma f naught by sigma f, I am just saying average, okay. So which is what going to give me sigma Ri is equal to sigma f average ln of, okay, of course this is inversed actually, Ri by R naught becomes R naught by Ri, and since I am going to update my sigma f, okay, by using this sigma f average, I am going to use R instead of R naught, where R naught is my initial outer radius, right. So that will get updated depending on what average flow stress I am going to take. So I am going to put R, okay. So that diagram is shown here. You can see this is just a simple schematic. This is one section of flange which is showing the movement, flange movement in the drawing. You will see that initially the flange region is up to this black part, so which is actually R naught, okay, and after some height, let us say height h, okay, after some flange, let us say cup height, so your cup wall height as let us say h, okay, the new radius is R. So this radius I am going to update it here. That is one small change we are having. So a simpler way to take strain hardening is to take an average flow stress value, okay, in the entire flange region, and that is going to change my equation to sigma Ri equal to sigma f average ln of R by Ri. Instead of R naught, I am going to put R by Ri. Okay. So now there are two things. One is strain hardening. Okay. We expect that once deep drawing happens, once it started happening, so flow stress will increase, and hence you need a larger drawing force, let us say, or radial stress. At the same time, R is reducing. At the same time, you will see that the material required for drawing is also reducing, because more and more you push punch down, more flange region is getting converted into your cup wall region, right, your cup wall. This is your cup wall region, okay, more flange region gets converted into cup wall region. So naturally R becomes smaller. So these two together is going to create one particular pattern of your evolution of sigma R, which is what is given in this particular figure. So for a strain hardening sheet, you will see that sigma R is of course plotted with height, this height, the height of cup, it is plotted with sigma R. You will see that initially there is an increment in the sigma R value in this way, and it reaches a peak value here. I represent it as a star, and then in further punch movement will actually increment in height will actually reduce the radial stress. This is how a typical plot would be for a strain hardening material. For a strain hardening, suppose the material is not strain hardening at all, then this your radial stress would be larger at the starting itself, because the flow stress will not get updated after that. So naturally it will be higher at the starting itself. That is how it will be. But for a strain hardening material, this is a typical nature of your radial stress. It will increase for some time, and once you reach a peak value, it is going to come down. And these two factors, your strain hardening and R becoming smaller together, is going to determine this evolution. So, this equation sigma Ri is equal to minus sigma F naught ln of Ri by R naught becomes this equation by considering an average flow stress, in a way taking care of your strain hardening effect. Okay. So, now how are we going to modify this equation? By including friction. That is the next part. So, when you speak about friction, so we are going to divide this further into two parts. One is effect on die radius. You can see that effect on die radius, I have mentioned this particular schematic which I shown you just before, and this particular location we are going to concentrate, and that is actually zoomed in here. Okay. So, you will say that in this the material is flowing this direction, it is already given, and your sigma Ri is acting in this direction, which we just now seen, and the sigma Ri can be converted into sigma phi, which is actually stress in the cup wall. Okay. So, stress in the cup wall is this. This is going to be your sigma phi. Okay. Sigma phi. So, sigma theta is circumferential, sigma r is radial, and sigma phi is nothing but a cup wall radius, stress in the cup wall. Stress in the cup wall. Okay. So, somehow this sigma Ri and sigma theta can be connected, and that can be done by this particular equation which we have already discussed. This was discussed in one of the previous chapters. We have derived this dt1 by t1 is equal to mu d theta, and in fact, if you integrate it between two different points, in between if you know the angular value, then you can integrate it and you can get tension in the new location with respect to the original location. Okay, we derived an equation for this, we worked out a problem also in this. Okay, so now the same thing can be rewritten in this way, d sigma phi by sigma phi is equal to mu d phi, and of course you can integrate it. Finally, you will say that sigma phi would be equal to your, sorry, this is phi actually, this is phi, this is also phi. So, sigma phi would be actually sigma Ri exponential mu into pi by 2. Okay. So, the angle, subtended angle is actually pi by 2 here. So, you will see that the coefficient of friction, Coulomb's coefficient of friction will come into the brackets. So, it will be same thing only, mu is going to be coming here and pi by 2. So, you will see that your sigma phi can be obtained if you know sigma Ri exponential times mu pi by 2. Okay. So, which can be obtained from this simple equation. So, this equation can be directly written, okay, without doing all these calculations also you can directly come out this equation based on your tension also, which you already derived. So, if sigma Ri is known from the previous equation, so we can get sigma phi also using this particular equation. Okay. So, sigma r can be found out, and from this you can get a sigma theta, which already done. So, from this you can also get a sigma phi, radial stress, circumferential stress. Now, this is a cup wall stress, stress in the cup wall. So, that is this part. Okay. So, now we are going to this particular location between the blank holder and the die, there is a flange region, and that situation is shown here, friction between the blank holder and the flange. Okay. That is actually zoomed in this particular schematic. So, this schematic basically tells you that, so this is your part of the flange region, you can imagine, this is part of your flange region. If you see this location, it is somewhere here, this location. This location is what is actually zoomed in here. Okay. So, now what we are going to say is, though in this analysis we have taken T is equal to T naught, so that there is no change in thickness, but originally in the schematic we have also shown that there is some change in the thickness at the edge. Okay. At the edge of the flange, you will see that at the edge of the flange here or at the edge of the flange here, you will see that there is some thickening that is going to happen, which is, that is why we said T plus dt, right. So, because of that, what we are going to say is, we are going to tell that this blank holding force, we are going to call it as B, is distributed around the edge of the flange as a line force. So, we are going to say that practically your blank holder is going to come down and hold the entire flange region. So, blank holder will have perfect surface contact with the flange region, and flange region will have full surface contact with the die surface. That is how practically it works. But for modeling point of view, we are saying that there is a blank holding force B that is going to act as a line force on the edge of the sheet. Why? Because basically there is an inclined surface here as I shown here. So, this thickness here is larger than this thickness. Let us say this thickness is T, this thickness would be T plus dt here. Okay. And because of that, it is quite acceptable to consider this blank holding force as a line force, but of value B by 2 pi r naught per unit length. So, B is a blank holding force. Okay. So, I am going to put a line force, that is B by 2 pi r naught per unit length. B by 2 pi r naught per unit length. I am going to put that here. So, that is why I plotted a downward arrow and then an upward arrow at both the surfaces. Okay. So, the material flow is going to happen like this. So, naturally your friction force is going to be opposing nature. So, I am going to write friction force as mu b divided by 2 pi r naught here and mu b divided by 2 pi r naught here. So, combinedly we can write 2 mu b divided by 2 pi r naught is a friction force. The friction force on the flange per unit length around the edge again is given by 2 mu b divided by 2 pi r naught. Okay. The same situation can also be represented by this sigma, okay, which is acting at the edge of the flange, which is nothing but this 2 times mu b divided by 2 pi r naught into T. Okay. So, the same thing, the friction force can be termed, can be written as stress acting on the edge of the flange, that is nothing but your sigma, as this 2 will be cancelled anyway, mu b divided by pi r naught T. Okay. So, I am going to write where T is my, actually it is T plus dt, okay, but it is understood that it is actually thickness at the edge of the flange, that is all. So, basically you have to use thickness at the edge of the flange here. So, I am just telling you that T plus dt for our explanation and T here, that does not mean that you have to use that thickness. So, you can use thickness here. So, thickness at the edge of the flange, thickness at the edge of the flange, okay, can be used here. So, mu b divided by pi t into r naught. So, I am going to say that stress acting on the edge of the flange, that means my sigma r at r is equal to r naught. Where is this diagram? My sigma r at r is equal to r naught at this particular location, okay, is given by this particular equation mu b divided by pi r naught t, where t is a blank thickness. So, now what I am going to do is my initial sigma ri is actually modified to sigma ri, okay, by considering an average flow stress, right. So, this is sigma ri. So, again this is also sigma r. So, I can add this part to this part to get the effect of friction into that equation. So, what I have done is here is we derived sigma r is equal to sigma of average ln of r by ri, right. So, the above equation, this equation I am going to modify like this. So, I am just going to add this part to this part. So, sigma ri is equal to sigma of average ln of r by ri plus mu b pi rt, where r is actually the changing radius, pi rt. Okay. So, now you will see that finally the sigma r, okay, which is nothing but the radial stress, has got some effect because of strain hardening, and then you are also bringing up your coefficient of friction, in a way lubrication effect, friction effect into this equation. Okay. So, this is the first level of sigma ri and this is the second level of sigma r. From this I am going to get next sigma ri by considering effect of mu, that is a third one, sorry, mu plus sigma f average, both. This is the third one. So, 3 different ways we have done actually. So, now this equation you say is radial stress for a strain hardening material with effect of friction. That way you can tell, and since sigma Ra is known to you, you can get sigma phi also. How do you get? You can just substitute it in this equation. Sigma Ra you substitute here. That means the entire sigma r is multiplied by exponential mu into pi by 2 to get the sigma phi, which is what I have given as sigma phi is equal to this entire thing, sigma f average ln of r by Ri plus mu b by pi RT into exponential mu pi by 2. Okay. In that way you can modify this equation. Okay. So, what are the things we got? We got sigma r, then we got of course sigma theta, the same sigma r can be used to get sigma theta also, alright. So, you assume a Tosca yield function, so you substitute here. So, sigma r can be used, this equation. Instead of this equation, you use the later equation into this to get sigma theta. So, what do we have found out is sigma r we found out, sigma theta we found out, and then sigma phi also we found out from all these equations. So, with the effect of strain hardening and friction. So, these are expressions for radial stress and cup wall stress, including strain hardening effect and friction effect. Okay. So, now there is one coefficient 1 by eta I have included, okay, multiply it 1 by eta just to take care of, it is like an amplification factor. So, some it is like an efficiency factor you can say to take care of any other approximation. Okay, like for example, the sheet gets bent and unbent, right, the sheet gets bent and unbent. So, that is not considered here, for example, because of this bending. Okay. So, initially it is flat, then it is bent, then it is again unbent. So, it becomes straight, right. Say for example, this is flat, it is bent here, then it is unbent to become straight, isn't it. So, this type of effects will also lead to some change in your stress value. So, just to get some efficiency factor, you can multiply with 1 by eta to take care of that changes. Okay. So, this value can be it is in our hand, we can decide it to improve the accuracy of this cup wall prediction. Okay. So, now in this last subsection of this in this discussion, there is going to be some relationship between this LDR, we are say LDR we said, right. What is LDR? We have said that as R naught by Ri. So, there is some relationship between this LDR and the material's anisotropy, that is sheet anisotropy. So, what is the connection? So, that is what we are going to see more in a very conceptual way. We are not going to derive much, rather what we are going to do is we are going to just discuss that in a conceptual way. So, from the previous formula equation we derived, this LDR actually depends on the average flow stress, we know that, and the current thickness B, and then maximum permissible value of wall stress, which is nothing but my sigma phi. Okay, average flow stress we said sigma F average, we brought it together, current thickness is T, this is your B, okay, and maximum permissible value of wall stress is sigma phi. Okay. So, there is a particular level of wall stress that is allowed when you do cup deep drawing, that is your sigma phi. Sigma phi is a stress in the cup wall, but there has to be a permissible limit. Okay. So, now let us discuss these points. If we neglect strain hardening during drawing, the maximum drawing stress will happen at the start of the drawing. This is what I was discussing with you before. If you do not consider strain hardening, then the simplest choice we have is drawing stress being maximum can be maximum at the start itself, because your flow stress is not going to increase beyond that. Okay. It could be the effect of R becoming smaller only. Okay. Two opposing factors we discussed, strain hardening and R becoming smaller. Now, strain hardening is not there, means the effect of R, radius becoming smaller, the material material required for drawing is reducing. So, R becoming smaller is the only thing which is going to determine. So, maximum drawing stress will be reached at the start itself. Now, we are going to put a condition, wall stress to initiate that drawing. Suppose if you want to initiate the wall stress, okay, what will you do? The simplest choice we have is sigma f is equal to y, which is becoming a constant, where y is our initial flow stress or yield strength, you can say. So, wall stress to initiate drawing or at the start of drawing, okay, the wall stress can be obtained by putting sigma f is equal to y, which is a constant in the previous equation. So, from the previous equation for wall stress, we can write now wall stress becoming, we are going to concentrate on cup wall now rather than flange. Now, flange is being converted into a cup wall. So, now what is happening in the cup wall is the main thing now. So, sigma phi is nothing but 1 by eta sigma f average ln of R by Ri plus mu b divided by RT into exponential mu pi by 2, right. So, what I am going to do is, I am going to put this condition into this equation, So, this I am going to convert that into y. So, I am going to say that general flow stress is going to become my yield stress, and I am going to say that my sigma phi is nothing but 1 by eta into y times of ln of r naught by ri plus mu b divided by pi r naught t naught exponential mu pi by 2. Only thing is like I am going back to my original dimensions r naught and t naught here, or because it is a start of the drawing, no. So we are saying that we asked us to initiate drawing, so which means that I am going to modify this equation into this is r naught and this is t naught. Okay. So this sigma phi, this sigma phi, this sigma phi. So in this equation these are the modifications I am going to put. So this becomes y. My sigma phi is, this becomes y, everything else remains same, and this related to original dimension. Okay. So now this wall stress has to be less than the load carrying capacity of the wall. So wall has got a particular load carrying capacity, no, you can imagine like that, and this sigma phi has to be less than that. And we have also seen before the cup wall actually follows plane strain mode of deformation. We have seen this example before in the when we discuss about the stress contour, strain contour, like we have discussed OA, OB, OC, OD, OE mode of deformation. Okay. So like this diagram you can see that we saw OB, OA, OB, there are 5 different we have seen 5 different stress paths we have seen. So in that we have mentioned this as an example that for a plane strain mode of deformation, the cup wall is the best example. So we have earlier seen that the deformation in the cup wall follows plane strain mode, and the stress at it would reach deform depends on the choice of yield criterion, and the stress at which it would deform depends on the choice of yield criterion. So we know that this cup wall stress should be less than the load carrying capacity of the wall. If that is the case, if that is the situation, then your cup wall should deform in plane strain mode of deformation, and it has to reach that particular value of stress, and that depends on what choice of yield function you have. Whether you choose Tresca or von Mises or any anisotropic yield function, yield locus. So it depends on that yield locus, which is going to tell you when that critical point is reached, for this sigma phi, So in that case we have shown here 3 different choices for this. What are the 3 different choices? You can see that this is for representation of Tresca yield locus, this is your von Mises yield locus, and this is some anisotropic yield locus. So in Tresca yield locus you pick up OP. So plane strain mode of deformation is actually OP. Plane strain mode of deformation in the cup. This is a loading path in the cup wall for various yield locus. Loci. This is a loading path. So you are going in the flange region, this is the way your stress is going to evolve. So it will start from O, it will reach P when yielding is going to start at Y, and you will see that sigma phi would be of this value. So same thing if you see from von Mises yield function, you start with O, you will reach P, and you will see that Y it is going to reach Y like this, and your sigma phi would be this much value. And if you pick up an anisotropic yield locus for which we are taking one particular case R greater than 1, R greater than 1. So true width strain divided by true thickness strain is nothing but your R, no? This is R is equal to this. So it should be greater than 1. Greater than 1 means what? So greater than 1 means, suppose like this ratio is 2, which means that the material is stronger in the thickness direction than in the plane direction, in the plane surface, right? So that's the meaning. So if you pick up R is equal to 1, generally you will see that the yield locus gets elongated in the right hand diagonal. You can see the elongation in the right hand diagonal in this way. And other things are same. You have OP which will reach it in this particular location, your Y is here, this much would be your sigma phi, this much will be your sigma phi. So this is what we were telling, that the stress at which it would deform depends on the choice of yield criterion. So when it is going to reach this particular point, actually is decided by the choice of yield function you choose. So now let us pick up all these 3 cases. We will discuss something which will tell us how this sheet anisotropy or the choice of yield locus changes the LDR calculation. So Tresca yield locus, it is pretty simple. Okay, for Tresca yield locus, the cup wall stress would be equal to y. So sigma phi is equal to y. We have seen this here. Your sigma phi would be equal to y only. The sigma phi would be equal to y. Okay. So now this particular equation which you have just now we have shown this equation. Okay. We said that to initiate your drawing. Okay, just to initiate drawing. Okay, then you have to put sigma f is equal to y. Then we have got y here, isn't it? So now what we are going to do is, as per your Tresca yield function, we are going to say that sigma phi is nothing but y. So this equation is modified to this form. Okay. So you can say that this sigma phi is nothing but y. Okay. So then eta can be taken here, y can come here, y can be taken inside. So this y vanishes and this y will come in the denominator of the second part. Okay. So I am going to get eta is equal to ln of r naught by ri plus mu b divided by pi r naught t naught, y will come denominator exponential mu pi by 2. So this is the condition for maximum sheet size. This is the condition for your maximum sheet size. So suppose if you use von Mises yield locus, okay, then we already know this particular equation, sigma phi is 2 by root 3 times y. Okay. This is plane strain. No? In bending also we derived this equation. In bending also, assuming it as a plane strain process, we derived this equation, sigma phi is nothing but 2 by square root of 3 into y. So now in the same way like what we have done in the Tresca yield function, you can substitute sigma phi in place of 2 by square root of 3 into y. Okay. So here you can see 2 by square root of 3 into y if you put, and then you calculate it, you will find out some eta value, and you will see that we obtain a greater LDR as compared to Tresca. Okay. So I have not worked out here, but you can just check it. We obtain a greater LDR. Okay. LDR would be slightly larger when you use von Mises yield function for the same material as compared to Tresca. Now when it comes to anisotropic yield function, okay, that means r greater than 1 case, which is the best case we have. R is equal to 1 indicates stronger in through thickness direction, and the main effect would be to strengthen the cup wall. Okay. So if the cup wall, okay, you are going like this, no? This is your axis, this is your sheet. So cup wall you are speaking about is this. Okay, this is a cup wall region, and the wall region is actually stronger. Wall region is actually stronger. Why? Because the thickness, through thickness direction strength is going to be larger than the plane if you take r greater than 1, which means that LDR would be greater in this case, as higher stresses are required to cause yielding in the sheet. So LDR would be much larger if you use an anisotropic yield function for r greater than 1 material. So in these two cases does not matter actually, r is equal to r is equal to 1 in both the cases, Tresca and von Mises, it's for isotropic material. No? So if r greater than 1 in this case is picked, then LDR would be larger. Why? Because there will be the material will be stronger in the thickness direction. So along with that, we should also note that along with strain hardening, cup wall strengthening is also important in influencing LDR. Okay. So though we say that your strain hardening is an important thing, okay, when we discuss about flange getting converted into a cup wall during deep drawing, in that analysis we consider strain hardening separately. That is why we made sigma f converted into sigma f average, right. But the point is, along with that, cup wall strengthening is also this strengthening. The strengthening is also important in determining the LDR. Okay. So the effect of anisotropy, sheet anisotropy, if you want to study, then we have to depend on the choice of yield function. Okay. Tresca or von Mises or any anisotropic yield locus for r greater than 1 indicates that if you have anisotropic sheet and if r is greater than 1, then somehow if you bring that anisotropy into the model, then LDR prediction would be accurate. LDR would be greater, we say, as compared to the other two, okay, when compared to von Mises and Tresca. And von Mises, if you compare with Tresca, it is we obtain a greater LDR as compared to Tresca. That is the way it is. So if you want to study the change in thickness of the sheet, okay, that is also possible. So this is just a brief note here. When the sheet is bent and unbent under tension, Okay, when the sheet is bent and unbent under tension, which is what is going to happen in your cup drawing, okay, which is what is happening in the cup drawing, right. So, in bending we have seen two cases, one is only moment and other one is stretching with with moment with stretching, right. So, bending with stretching we have seen, but in this case actually there is no other choice, there is only under tension only because the sheet is gripped. Okay. So, because of this bending and unbending there will be reduction in thickness, and that is given by this particular equation which we have not derived. This is for our understanding only. Del T by T would be equal to minus 1 by 2 rho by T into T by Ty, where del T is nothing but your change in thickness and all other terms are known to us. Rho by T is nothing but your bend ratio which you already introduced. T is your tension and Ty is the yield tension which we introduced in the bending chapter. You will see that from this equation a small bend ratio rho by T will increase the thickness reduction, and that is going to reduce the load carrying capacity of the die wall, and it is going to reduce the LDR. Okay, from this relationship we can find one important relationship. From this equation we can find one important relationship between bend ratio and del T. Del T is connected to LDR. That is the way we are connecting. How is the relationship? For a small bend ratio, okay, that is in the denominator, let us say, it will increase thickness reduction because in the numerator by reducing the load carrying capacity, okay, of the die wall, and it reduces the LDR further. So, if load carrying capacity of the die wall is reduced, which you have seen in this particular diagram, your LDR will reduce. Okay. So, it is appropriate in a way to tell that the largest blank that can be drawn is a 2.72. If that is the case, okay, it is an extreme case, but it will be less than 2.72. Generally, it is between 2 to 2.2, which is what I told. You take eta value of 0.2 to 0.7 in that equation to get LDR. That is the best option we have. Eta value we discussed now is eta. Okay, just to summarize, to have a better LDR, we need to follow this particular thumb rule. Okay. So, if you want to have an improvement in LDR, then R greater than 1 is preferred. Okay, that means anisotropy of the sheet is existing, means you have to consider that anisotropy. Okay. If we have R greater than 1, then LDR would be better. And rho by T has to be larger. If rho by T is larger, delta T would be less. Delta T would be less means you will have a better LDR. Okay. And mu has to come down, and your coefficient of friction has to come down. That means you have to put appropriate lubrication to improve the LDR. So, these are some of the important thumb rules we can get. Okay. So, we stop here, we will discuss it further.